Hello everyone. My presentation today is Sociotechnical System Collaborative Interactions in Complex Tissue Structures. Before reporting on today's main lesson, I would like to explain the conceptual origin of sociotechnical systems. What is a social system? A sociotechnical system is a systematic view of an organization. It was proposed by Tester, Trist, AEL, of the Tavistock Institute for Interpersonal Relations after a study of the operation organization of coal mining sites in Durham, UK. The theory that the organization is formed by the social system and technology system interaction of social technology system, which formed by a variety of factors, the social and technical elements, collaborative interaction to achieve the best function, emphasize the social system cannot exist independent of technology system. Technology system changes can also cause social system changes. Although this is a theory of management, it has now been applied in various fields, including software engineering. In these areas, understanding the complex interactions between human causes and technology components is essential for successful project development and deployment. In software engineering, sociotechnical systems summarize the dynamic interactions between social and technological components within an organization. These systems recognize that effective performance stems from the integration of human capabilities, organizational structure, and technological tools. The combination of multiple parts makes the function of the socio-technical system beyond the sum of these parts, and the human-centered design as the most basic principle. In the early Industrial Revolution, from the end of the 18th century to the beginning of the 19th century, the Industrial Revolution promoted the initial formation of social and technological systems, and mechanized production became the mainstream. Technological innovation in the information age. In the second half of the 20th century, the popularization of computers and the Internet marked the entry of social technology systems into the information age, which greatly changed the mode of work and life. At the beginning of the 21st century, with the attention of environmental issues, social technology systems began to integrate into the concept of sustainable development and to promote the development of green technology. This is the origin and the development of socio-technical systems, and I hope you have an understanding of that. The following is the content of our topic today. In the first part of today, we will explain the basis of the socio-technical system, in which we will mention 1 definition and importance of the system, 2 system classification, 3 hierarchy of social systems, 4 factors affecting socio-technical systems. The second part is system properties and the properties, where we will understand the 1 characteristics of socio-technical systems. It includes emergent property, non-deterministic, and success criteria, and 2 system properties. The third part is system engineering and management. In this part, we will learn about 1 system engineering dot. This includes system procurement, system development, and system operation, and 2 problems in system engineering, which includes human error system and the evolution legacy system dot. And in the last section, we will discuss human factors and ethics in the design of social systems dot. Now let's get started. The first part of today is the basis of the socio-technical system, definition and connotation. To understand the socio-technical system, we need to know what a system is. A system is a collection of diverse components intentionally related to achieve a goal. The complex systems are even more complex, and they are often layered out of multiple systems, each part of which has closely related properties and behaviors. The successful operation of each system component depends on the operation of the other components. Now we can note that social-technological systems are complex organizational structures containing social and technological elements. These systems interact to cooperate for optimal function. Emphasize the interdependence of people, processes, and technology. The importance of socio-technical systems' human-centered design. The system design should be consistent with human ability, needs, and behavior, flexibility and adaptability, enabling organizations to respond to changes in the technological and social environment. Participatory decision-making. Ensure that both technical experts and stakeholders are involved in the decision-making process. Continuous improvement. Encourage organizations to develop and optimize their systems over time. Generally speaking, system classification is divided into technical computer systems and socio-technical systems. Technical computer systems. The system contains both hardware and software components, but lacks procedures and processes. Technical systems include TV sets, mobile phones, and other devices containing embedded software. This category also includes most PC software and computer games. Individuals and organizations use technical systems for specific purposes, but the system itself does not understand these purposes. The socio-technical system. These systems contain one or more technical systems, but also contain people who understand the internal use of the system. The social-technical system has the established operation process, and the human operator is the basic part of the system. They are subject to organizational policies and norms, which may be influenced by external restrictions such as national laws and regulatory policies. Now let's look at the hierarchy of socio-technical systems. We usually divide them into 7 layers, called the equipment layer, contains hardware devices such as computers and sensors, which are the material basis of the system. The operating system layer interact with hardware to provide a general set of common functions for the more advanced software layer in the system. Communication and data management layer enhance the functionality of the operating system and provide interfaces with the more advanced functions, such as remote system access, system database access, etc. Application layer provides specific application functionality and may include multiple applications. The business process layer. At this level, develop and implement organizational business operations that use a software system. The organizational layer contains higher-level strategic procedures and company rules, policies, and standards that must be followed with the operating system. The social layer, social laws, and regulations that regulate the operation of the system. We should know that systems engineering is the process of designing the whole system, not just the software in it. Although they are relatively independent, we need to evaluate the security and reliability of the software as a whole, rather than consider the software or a certain level as a separate part. At the end of this section, we look at factors affecting social technical systems. 1. Commercial objects. Social technical systems are enterprise solutions that help achieve business purposes. This property allows organizations to respond quickly to external changes and remain competitive and relevant. Because they are integrated in an organizational environment, the procurement, development, and implementation of systems are influenced by organizational rules and processes, and even the work culture. This commercial purpose makes the social technological system enough to adapt to change, whether it is technological progress or the evolution of social needs. Point 2. Organizational environment. Socio-technical systems emphasize the synergy between different components, including people, processes, and technology. Therefore, the organizational factors coming from the system environment may affect the needs, design, and operation of a social technology system. When developing a social technology system, you must first understand the organizational environment in which the system will be used. If you don't understand, these systems may not meet the business needs, and users and management may reject the system. Organizational factors. Process change. Because of organizational changes, the system may need to adjust the workflow in the environment. New changes have made the training a necessary project. If the change is large or involves personnel unemployment, users may resist the implementation of the system. Job change. The new system may lower users' skills in the workplace or prompt them to change how they work. If this happens, the user may proactively resist the implementation of the system within the organization. Managers often dislike the need to adapt their working methods to the design of new computer systems. Managers may think that the system is reducing their position within the organization. Organizational change. The system may change the political power structure of the organization. For example, if an organization relies on a complex system, the person who controls access to the system will have significant political power. Part 2. System properties and properties. 1. Characteristics of social technical systems. The emergence of characteristics. System features are holistic, determined by the components and their interactions, and can only be evaluated after the system is created. Uncertainty. System behavior may vary from operator to operator, resulting in the temporality of system defects and failures. Ability to serve your organizational goals. The ability of the system service target depends on the stability of the target and the interpretation of the people within the organization. The emergent features are system-wide and not component-specific. Emergent quality is determined by the components of the system and their interactions. Given this complexity, emergent properties can only be evaluated after the system is created. Security and reliability are the emergent system features. Functional emergent quality appears when the functionality of the system is displayed only after its components are integrated. For example, a bicycle has a functional property as a vehicle after its components are assembled. Non-functional emergent properties involving the behavior of the system in its operating environment. Emergent quality includes reliability, performance, safety, and security assurance. These are critical for computer-based systems, and failure to reach the minimum specified level in these attributes often innates the system. Some users may not need all the functions of the system, therefore, even without the system. But if the system is unstable or too slow, all users are likely to reject it. The emergent reliability characteristics. Reliability is determined by the properties of each component and its interconnections. System components are interrelated. Failure in one component can propagate throughout the system, affecting the operation of the other components. However, it may be difficult to predict how these component failures will affect other components. Therefore, it is almost impossible to predict the overall system reliability by using only the reliability data of the system components. So how to enhance the system reliability? Ensure the hardware reliability. How likely is the possibility of a hardware component failure? And how long does it take to repair a failed component? Software reliability. How likely are the software components to generate inaccurate results? because software failures are usually temporary. The system continues to run even after generating inaccurate results. Operator reliability. How likely is the system operator to make mistakes and enter the wrong data? How likely is the software failing to identify and spread errors? Second, uncertainty. Socio-technical systems are non-deterministic, partly because they contain humans and also because of the very frequent changes in the hardware, software, and data that occur in these systems. The interconnectivity between these changes is complex, and so is the behavior. 3. Success standard. Complex socio-technical systems are built to deal with so-called thorny problems. Rittel and Weber, 1973. A thorny problem is a problem that is very complex and involves many interrelated entities, without a clear definition of the problem. Different stakeholders view the situation in different ways, and no one has a full grasp of it. The actual nature may only manifest itself when the solution is created. Therefore, it is difficult to judge whether the socio-technical system is designed successfully, which usually depends on the stability of the target and the interpretation of the personnel within the organization. The third part, system engineering and management. 1. System engineering. Systems engineering refers to all the activities of the purchase, specification, design, development, verification, deployment, operation, and maintenance of a socio-technical system. System engineers focus not only on the software, but also on the hardware and how the system interacts with the user and its surroundings. They must consider the services by which the system provides, the constraints under which the system must be created and operated, and how the system can be used to achieve its goals or tasks. Procurement or acquisition. This stage determines the objectives of the system, establishes advanced system requirements, determines that functions will be distributed across hardware, software, and personnel, and purchases components of the system. Develop. The system was constructed. The development program covers all aspects of system development, including requirements definition, system design, hardware and software engineering, system integration and testing. Operational processes were specified, and training courses for system users were designed. The system is deployed, the users are educated, and the system is in service. The proposed operating procedure is usually modified to reflect the actual working environment used by the system. The system evolves over time as new requirements emerge until it is abandoned. Challenges faced in systems engineering. 1. Factors that affect the safety and reliability. Each stage of systems engineering affects the safety and reliability of the system. Question. 1. Procurement decisions may limit design choices and affect the installation of system protection measures. 2. Manual errors in the specification, design, and development stages may lead to system problems. 3. Inadequate testing may leave the defect undetected before deployment. 4. Problems during the operation may lead to further vulnerabilities. 5. System operator errors and hypothesis. Forgetting when implementing system changes may introduce new vulnerabilities. 2. Challenges involved in the multi-professional areas. Systems engineering involves a variety of expertise with increased complexity. Main points. Differences in communication between different disciplines may lead to misunderstandings and vulnerabilities. Capability assumptions based on one-sided understanding may lead to poor design decisions. Interdisciplines may advocate for inappropriate solutions because of protecting professional boundaries. System procurement. System procurement, also known as system acquisition, is the initial phase of system engineering. At this stage, the scope of the system to purchase, the system budget and schedule, and the advanced system requirements are selected. Using this information, further judgments are made about whether a system needs to be purchased, what type of system is needed, and who will provide it. Next is some purchasing decision drivers. 1. Replace existing systems. Replace systems that are difficult to interact with or expensive to improve commercial revenue. 2. Compliance with external regulations. Ensure that the system complies with external regulations, such as Sarbanes-Oxley accounting regulations. 3. External competition. Invest in new systems to improve the efficiency of business processes and maintain competitive advantages. Business restructuring. To adapt to the new process after enterprise restructuring and implement the new system. Available budget. The budget limits the breadth and depth of the new system procurement. System procurement process 1. Off the shelf with custom components. Large complex systems often cons off a combination of off-the-shelf and custom components. If not customized, the selection system needs to determine the best match between the system requirements and the capabilities provided by the off-the-shelf system. The preconditions may subsequently need to be changed. This could have a ripple effect on other systems. 2. Contract for purchase. Specify specifications for the custom system included in the purchase contract, which is both a legal and a technical document. 3. Contract negotiation. Discuss the additional requirements and costs with the contractor and negotiate the costs and license terms of the COT system with the supplier during the contract negotiation period. Problems in procurement, suppliers and subcontractors. The software and hardware in the social technology system are usually produced by different organizations, suppliers, than the company, customers, that buys the whole social technology system. System suppliers usually outsource subsystem development to subcontractors to form a single purchaser-supplier interaction. The impact of purchasing decisions. Procurement decisions have a significant impact on the safety and reliability of systems, especially when selecting off-the-shelf systems or customized systems. Additional development time and budget may be required if the required reliability and acceptable system performance are to be met. System development. System development objective. That means develop or acquire all the components of the system and combine them into the final system. Demand constitutes the link between the procurement and development processes. There are some system development. Stage 1. Demand development. Clarify business and advanced functional requirements in detail and determine priorities. System design. Determine the system architecture and understand the relationship between components. 3. Subsystem engineering. Build software components, configure off-the-shelf hardware and software, and design special hardware. System integration. Assembling components to showing emerging characteristics. System test. To find and solve problems, improve performance, and integrate new requirements. System deployment. To provide it to the users, migrate the data, and connect to other systems. Then, there are many considerations in the development process. Plan-driven technology. Since multiple parts are created simultaneously, requirement understanding is critical. Therefore, the system requirements must be thoroughly understood before any hardware development or build activity begins. The spiral development of demand and design. Demand development and system design stage are closely related, and the two influence each other to form a spiral development. Multiple options to meet the requirements. Multiple design options should not only be appropriate for the continuously developed technology solvers, but also consider organizational and political considerations. Parallel building and integration. Implement the hardware and software components of the system. Build subsystems in parallel and submit system modification requests when facing cross-boundary problems. Software expediency is often required. Subsystems. One system integration. the independently constructed subsystems are combined into a complete system. Main points: 1. Integration strategy includes comprehensive integration and stepwise integration. 2. Progressive integration reduces the cost of error detection, but may expose errors between subsystems. 2. Throw down the gauntlet tests performed during and after system integration and possible problems. Main points: the test focuses on component interfaces and system behavior, exposing subsystem problems. Subsystem defects may lead to a disagreement between the contractors. There are some tips. System delivery and deployment. End of the system development process, including installation, data migration, user training, and existing system adjustments. But complex situations that can occur during deployment, such as user environment differences, data cleaning, and interface issues. We need to adapt the existing systems in the environment to ensure that the new systems can communicate with them. Reliability and safety. We should focus on the impact of system development methods on reliability and security, as well as the trade-offs between price, schedule, performance, and reliability, while also trying to avoid system failures caused by human error and possible inadequate system testing. Now let me conw about system operation. Steps to using the system to achieve its intended purpose. Such example: management procedure of air traffic control operator. Tips. 1. Planning and training of the operation process. 1. The operating process must be defined and documented during the system development stage to facilitate the detection of problems. 2. Operators' training and workflow adjustment are required. 2. Unique ability of the operator. The operator is able to cope with unforeseen situations, recover situations, or even violate established processes to accommodate actual conditions. 3. Flexible and adaptive operation process. Create operation processes that do not strictly rely on a specific order, allowing the operator to improve according to the actual situation. 4. Challenges for the simultaneous operation of the old and new systems. We need to timely detect the physical incompatibility, data transmission problems, and user interface differences that may result from the new system running simultaneously with the existing system. Problems in system engineering. 1. Mistake system failure due to improper operation of technicians. 2. Phylogeny. Large, complex systems will evolve throughout their life cycle to adapt to environmental changes and new demands. 3. The legacy system. Legacy systems are systems that use outdated technologies and are difficult to change but business critical. Solutions to human error. Usually we have two ways: individual method or systemative method. The first way holds that individuals are responsible for their mistakes and that unsafe behavior, e.g., operator failure to activate the safety barrier, is the result of negligent or irresponsible behavior. Human error can be reduced by taking disciplinary action, process strengthening, retraining, and other measures. Next way is systemative method. This approach holds that a good system should acknowledge the possibility of human error and provide barriers and protective measures to identify human defects and allow the system to recover before a failure occurs. When a failure occurs, the choice is not to find someone to blame, but to understand why the system's defense failed to detect the error. We take the second as the correct choice. So how can we protection against human error? 1. Foreseeability. Designers should anticipate the obstacles in the technical components. 2. Process designers should transform the solution into part of the system process and procedure. 3. Personnel can be operated. If solutions cannot be translated into the process, designers can translate these problems into human input solutions to provide a judgment guide to the operator. We're going to talk about a concept here, reason, the Swiss cheese system, fault model. Explain how the system protection measures and potential conditions can lead to the system failure. The model believes that the organization activities in the accident and environmental impact, unsafe supervision, unsafe behavior precursor, unsafe operation of 4 level factors. Each level represents a heavy defense system. The level of the hole represents the loopholes in the defense system. The position of the hole, size is not fixed. Unsafe factors, like a constant light source. Each level of the hole at the same time in a straight line. Danger will be like a light source, instantly through all holes, lead to the accident. Tip: designers should create a system with multiple barrier types. This means that the holes are likely to be distributed in different locations, reducing the possibility that they fail to detect errors in the hole alignment. Next is phylogeny. System evolution refers to the process in which large and complex systems are constantly modified and expanded to adapt to environmental changes during their long life cycle. These changes include fixing defects in the original needs, meeting new needs, replacing faster new hardware, adapting to changes in the use style brought about by organizational restructuring, and responding to changes in the external environment. System evolution is conducted in parallel with the normal system operation process, involving the redevelopment and adjustment of hardware, software, and operation process. Designers should maintain the scalability and flexibility of the system to adapt to future modifications and changes. Finally, we talked about the legacy system. What is it? Business-critical social technology computer systems using outdated technologies, including hardware, software, and processes. Throw down the gauntlet one. Business-critical. Legacy systems are critical to the business and have a high risk of replacement. Second, technology dependency. Changing one part may affect other components, resulting in a chain reaction. Prime cost 1. Thoroughly analyze 2. Subsystem interdependence 3. Design decision records 4. Damage structure 5. Reliability and safety issues 6. Test and maintenance difficulties. We come to the last segment of today, human factors and ethics 1. We need to think about the interplay of the social and technical elements. If designers want to understand the interplay of social and technical elements in software engineering, it is to recognize the close connection between technology development and human factors. So we need to focus on the impact of team communication, collaboration, and organizational culture on projects to promote the success of software projects. Issues of concern in the design. That's human-friendly type. Designers should focus on research and considerations on how human capabilities, limitations, and behavior influence the design, development, and use of software. This includes user interface design, user experience, cognitive ergonomics, and programming psychology. Understanding human factors is critical to creating software that is user-friendly, efficient, and meets expected user needs. It involves considering usability issues of concern in the design. Ethical considerations in software engineering involve the identification and processing of the ethical implications and responsibilities associated with software development and deployment. This covers aspects such as user privacy, data security, transparency, and the impact of technology on society. The task of a software engineer is to make decisions that influence both individuals and the community, and ethical considerations guide those decisions. It involves avoiding bias in the algorithm, ensuring fair treatment of users, and considering the social impact of the software application. Ethical considerations also involve transparency in the software development process, responsibility for the consequences of software decisions, and a commitment to create technologies that fit ethical principles and values. By incorporating ethical considerations, software engineers contribute to the construction of a trusted and responsible technology ecosystem. At the end, let's summarize. Socio-technical systems are a complex of computer hardware, software, and people designed to help organizations achieve their goals. Human and organizational factors have an important impact on the operation of the system and the emergent characteristics of the system, e.g., performance, reliability, availability, and security, determine the success of the system. System engineering includes 3 stages: system procurement, system development, and system operation, focusing on system integration and adaptation to business changes. In addition, the system should have an error protection mechanism to prevent human error from failure, which is described in the Swiss cheese model. Thank you.